This. Yep, so I'm Richard. I have been defining WebAssembly or parts of WebAssembly in the K framework, supervised by Magnus, and with a lot of help from this guy, Everett, at Runtime Verification Incorporated in Illinois. And so the title is Semantics of WebAssembly in the K framework. I assume most of you are familiar with semantics, maybe less so with WebAssembly in the K framework, so that's what I'll be digging into. First I want to give you a bit of background, just how I ended up here. Then I'll go through K, then I'll go through WebAssembly, and I'll try to do a live demo of implementing a little bit of WebAssembly in K. And if there's time, I want to get into proving things. It's not any big proofs I want to show you. That could be a talk in itself, proving things in K. But if anyone's interested in more and there's not time, just stick around or grab me at any time or ping me and I'll be happy to show you what I know. But to pick up on Wolfgang's point, how did I end up doing WebAssembly in K? Well, I was interested in smart contracts, in Ethereum in particular. I'm very interested in blockchain technology. I think smart contracts is a really interesting field if you're interested in formal methods, because you want to do high assurance code because you're publishing it publicly. You can't patch it, and there will be a lot of people out there looking at your code trying to find a bug so they can steal all your money. So if you can verify it, then that's usually a good approach. So I started looking for examples of this in the Ethereum community, and I came across, I have some people, some friends working at a company called MakerDAO. Most famously have something called a stablecoin, which is they use game theory and economics to make a crypto token that follows the US dollar. Really cool. But they have also verified the core contracts of this DApp, this distributed application. And the people who have done most of this verification is tied to an organization called DAppHub. So I reached out to them, and it turns out what they've been using mostly is the K framework, mostly maintained and used by a company called Runtime Verification. And the reason, so what I learned is that sort of K has become a de facto standard for verifying smart contracts on Ethereum and K-related tools. And the reason is, they have a nice specification of the Ethereum virtual machine in K. The Ethereum virtual machine is a pretty simple stack-based machine. It deals with some complex world state, but all in all, it's a stack machine with 120 opcodes. A lot of them are just like repeated ones, like access the first stack element, access the second, access the third, and so on, down to 16. So it's not that much. And so, as you can see, Everett, that I mentioned in the beginning, is the first name on this paper. When I talked to him, it turns out he has been starting work on doing a similar formalization of WebAssembly. And it might not be obvious why, but it's because Ethereum is thinking about moving from their own virtual machine into a more a one that's used has wider use. So basically, Wasm. They want to have Ethereum running using WebAssembly as their virtual machine. And there's all these ideas that this would be better because it's supposed to execute faster because you can make use of all, the entire WebAssembly community and all their work on their virtual machines. It's a pretty efficient format. It has some nice security features, like there's no jumps. You can have it's better for high assurance things. This is really cool. So the idea is that much like WebAssembly, you want to escape having to write all your web code in JavaScript. It would be cool to be able to write your smart contract code in languages other than Solidity and Viper and Flint and so on. So use your general purpose languages and be able to write smart contracts with them. Wasm lends itself pretty well to static analysis, metering, and portability. So ideally, you would be able to run your Ethereum client on your phone or an IoT device or wherever you can have a Wasm interpreter running. So with that, I'm going to go into a brief introduction of the K framework. I don't know how many of you are familiar with it or have heard of it or seen it or tried it, but a little bit. So, well, here's the vision of K. Like how they're always pitching it. You want to be able to define your language once, right? You want to give the syntax and you want to give the semantics, and then stuff should just follow. I mean, you get a parser, you get an interpreter, a compiler, the standard stuff. But also, you should get a bit of this. You should not have to assign a grad student to spend X many months on implementing a model checker and doing symbolic execution and so on. Ideally, that should just follow from your specification. So when you define the language in K, well, you get the parser, you get an interpreter, you get a debugger, and you get this, which is what we use for smart contract verification. They've developed something they call reachability logic. There's a paper on it in the references, which is, they've shown that it's sound and relatively complete. So it's pretty cool. They've specified a bunch of languages in K. So, I mean, and not toy languages, real languages. So Java 4, C11, JavaScript, EVM, some other ones, some works in progress. So, I mean, it's an industry-grade tool. Runtime verification do use this extensively to actually verify real code. And I've been saying, specify your language in K. What does it mean to specify a language in K? Well, you need three things. You need a syntax. It's pretty straightforward. And then you have this idea of state, which is your execution state. It's called a configuration. You can think of it, it's pretty monadic. It's just a state that's always getting passed around as you're applying your operational semantics. And they're specified as rewrite rules, which looks a lot like functional programming with some quirks. Specifying syntax in K is pretty straightforward. I'm going to use a toy example of an imperative language. Has expressions and statements. It's regular Bacchus-Naur form. You have a few nice annotations that make your life easier. So if I say bracket, that means these parentheses are not going to show up in any abstract syntax tree. It's just a way of grouping things. And this little arrow just says, well, everything here takes precedence over this. We're going to have statements. They're going to be identifiers, assignment, expression. So nothing fancy on the left-hand side. We only allow identifiers. We can have a sequence of statements, and we're going to return things. And here's an example of a simple program that would be in this language. And we're going to use this, going to execute this as an example. So you see, it has an assignment. It has an axis in the right-hand side of the assignment. Secondly, you want the configuration. So for this example, we're going to say we're going to have an environment and a store. The environment is going to map variables. We're going to have a heap of variables and a heap of values, and the variables are just going to point positions in the heap. And the configuration always contains this thing. It's called a K cell. So your program, your set of instructions, is just part of your running state. So as you're executing, you can match on any part of your state. So matching on a single statement is the same as matching on anything else. Well, if you want to rewrite part of the store for an optimization or a garbage collection simulation, for example, you write those rules the same way you would write regular program transitions. Always forget those. Here's an example of a rule, like the operational semantics. So in this case, we would say, if we match a situation where the configuration looks like this, there's an identifier at the top of the K cell. These dots means there's more stuff here. But we're saying at the top of the K cell, we see an identifier. We rewrite it. This means rewrite to V. And what is V? Well, that depends on the rest of the configuration. So X is in the environment. It points to a store location. That store location points to a value. So we're going to replace the identifier by its value.
Sorry, the ... is intentional.
Yes.
Right.
So yeah, this is actual syntax. So there's this, I'm going to show you real quick. There's this little squiggly arrow. So the ... means like we have something on top of the cell, and then there's everything else after. We could also match on that explicitly and say, this is going to rewrite to V, like we match on this and everything else, and we rewrite that to V and everything else, but this is just idiomatic.
I think in environment and store, you match on a multi-set, I think, right? This X is an element in a multi-set.
Yes, exactly. So this is a map, and that's a map from
right. That this mapping from X to SX is part of a multi-set, and with this dot you can match.
Oh yeah.
Every multi-set which has that.
Yeah.
Map.
Exactly. So you're saying, so the contents of this cell is associative, so we only can put dots here, and this is associative and commutative, so we can put dots on both sides. Basically, this is just a way to access the elements of map. And if we just run this example program, we will take this program, we will parse it, and the initial configuration will be, we're going to start with, I'm not going to declare any variables here, we're just going to assume we start out with them in the environment. If we wanted aliasing, we could have a third variable called C, and if that points to the same place as A, they're going to write into the same place in the store. So I'm going to skip a bit of magic as well, so I'm not going to go into how the expressions are evaluated and so on. So that's going to get rewritten to A assign 6. This rule is going to match the assignment, which means we're going to write 6 into A points to 0, 0 points to 0, so 0 is going to get replaced by 6. This one's slightly more interesting. So you see we have A in here. What we're going to do is there's a bit of magic going on here. It's pretty straightforward to do, but I'm not going to go through it. But if we encounter that, just put A at the top of the stack, evaluate it with a variable lookup, and then plug it back in there. Finally, we have a variable assignment that matches this rule, and 17 is going to get plugged in there. And we end up with a final configuration that looks like this. If you want, you could add a rule here that handles return in some way. Maybe you want a return cell in your state saying, usually what you do is you're supposed to run your program until the K cell is empty. But the idea of K is you specify your semantics as, here's your initial configuration. It's going to go into, it's going to evaluate into a final configuration. And then it's up to you to decide if you want to process that further or if that's what you want to match on. That's the introduction to K. Any immediate questions or anything unclear? It was very hand-wavy and brief, but it gives you an idea of what it is to work with in this. Also, brief introduction to WebAssembly in case you're not familiar with it. Like Alejandro quoted, I think, one of the creators of WebAssembly. They said it's not web and it's not assembly, but it's a great way to sell it. And it's been working really well because people are really excited about it. But it's a cool, lowish level language, but it has so it's designed to be fast on hardware, but it's not specific to any architecture. You can stream compile it, which is of course really nice on the web. You can compile it as it comes in rather than having to load all of it. It has an efficient byte format and also pretty readable text format. It doesn't really hurt that much to code in it directly. Nice safety features, no arbitrary jumps, which is really nice. So it has blocks, loops, and breaks. So again, it's not really assembly, but you can only break out of the loop you're in. You can't just jump anywhere, for example. Allows a lot of static validation, no implicit cast. You always know what type you're working on. Running a WebAssembly program is first parsing it, then validating it. You can see that, well, this is not going to fail in any undocumented way. Nice safety features. It's organized in modules. I like to think of it as sort of like, in Java, everything's a class. In WebAssembly, everything's a module, so you have to put everything in a module. Inside a module, you can declare functions, you can allocate memory, and so on. You can export and import from other modules. You can only modify the things you have imported and the things you have declared. And if you want to just run your WebAssembly program without calling it from an external environment, you just you can define a module can have a start function, an init function. So if you want to simulate the Java way of doing things, you create a module called main and you make a function called main and you say, well, when this module is loaded, call that function. And talking about how it's actually pretty nice to code in. It is stack-based, so it's like a stack-based machine with opcodes, but you can fold it into X expressions. So it's actually pretty neat to work with. And I'm going to give an example of that. So in a regular stack-based way, you say, well, if I'm accessing memory, I want the memory size. That's an auxiliary function, so that's going to put the current. My module has a memory in it. Give me the size, put that on top of the stack. That's going to be an i32, so I need to make an i64 of it. I'm going to access my local variable, TMP, put that on top of the stack. And then I'm going to go into my memory and load 1 byte, interpret it as unsigned, make that an i64. So now I have 2 i64s on top of the stack, and I do add. So this is how you code in a regular stack-based machine. But you can also do it like this. So add takes 2 arguments. The first argument is this function takes a single argument. Second is a function that takes this single argument. So you can write it as if you're just calling functions. And you can mix it. You also often want to do that so you don't get this pyramid of doom thing going. So I can call this function in a folded way, this function in a folded way, and then just add them in a stack-based way. Just to give you an example of what an actual piece of code that does something might look like, here's a module that declares a memory and a function. By the way, the syntax highlighting here is scheme because there wasn't any WebAssembly highlighting, but that emphasizes the point of it's pretty nice to work with the S expressions. And an example of a function would be this just does some silly things. We export it so other functions can invoke it with this name. It takes 2 parameters, an i32 and i64, results in an i64, and we declare a local variable. And what I'm going to do is I'm going to grow my memory a little bit. I'm going to get the result back is going to be the old size of the memory. I'm going to multiply that by the page size. Memory is defined in 64 kilobyte pages of bytes. And I'm going to store that in my temporary variable. So after I've grown the memory, this local here is going to point to the first location in my newly allocated little page of memory. And there I'm just going to store a variable. You don't have to comprehend. I'm not going to go through this as an example. It's just like an example of how actual WebAssembly code would look like. So I'm going to store a value there. I'm going to load. Here. I'm going to get the current memory size. I'm going to load a single byte from the place where I stored something, and I'm going to add those together. And as you see, this final thing is going to leave something on the stack, which means that this function validates correctly because it expects a single item to be at the end at the top of the stack in the end. So if we were
the top of the stack is the results. Kind of.
Yeah, exactly. So and currently, so the syntax allows you to have several results. But currently, in 1.0, the same thing. The syntax allows you to have several memories. But in version 1.0, there's always just one. So there's a lot of these things like, in the future we may allow this, but right now we only allow one return value. So if you return anything, then you just leave something of that type at the top of the stack. And if I said i32 here, this wouldn't validate. So that's nice. You can statically see that, this is you're leaving something of the wrong type at the top of the stack. And this would work even if I had complex loops and breaks going on. We don't have to go through how the program runs, but in this case, it would just grow the memory by 2 pages twice, and then get something from the memory and load it. It's not important. The specification, which I have here, if anyone wants to browse through it later, is really nice. So Everett has been working with the yellow paper for Ethereum, which is pretty terse and also kind of ambiguous in places. The WebAssembly specification is really nice to work with, fairly unambiguous. And all the execution rules comes in 2 flavors. You get this nice logic rewrite rule types operational semantics, and you get a nice formal but still prose explanation of every operation. So here's an example of the memory size operation. If the program is a store, a frame, and a memory size operation, replace that by the same store, the same current frame, and the size. And then you can go into the store, you see there's a bunch of memories in the store. You access the memory that corresponds to f.module.mem address 0. Remember, we only have one memory at every time, so you're always implicitly working on mem address 0. But in the future, you might be able to work on different memories and specify which one you're working on. You take the length of that data and you divide it by 64 kilobytes, and that's your size. So that's going to be returned. Oh, sorry. The store might look like this, or the store actually looks like this. So in the store, there's a bunch of memories in your current frame, which holds like your current execution context. You're going to have a module instance, and in that module instance, there's going to be possibly an address to a memory, which we use here. And this can also be validated beforehand, I think. So you'll never be able to do memory size if you don't have actually imported or allocated a memory. And of course, you get these nice descriptions that are still formal. I like to read them first and then go over the rewrite semantics. It just describes in words what the operation does. Cool. Any questions on WebAssembly in general? All right, then I'm going to try and jump into just actually implementing one of, or a few of the operators that I have been working with. Can everyone see this okay? Does anyone need to jump closer?
Do we need to switch off light a bit?
Oh yeah, that's probably a good idea. Oh, just to simulate the actual workflow. So first we're going to do, I've started with defining a few things. So this is a K module. I call it Wasm. I import domains. That's basically say import the standard library with K. I've defined a small piece of configuration here. We have a K cell, and you shouldn't see that. It's for later. And I have a stack, and then I have so in WebAssembly they tend to see, what they do is they leave the constants on top of the stack, and so if you would do an add operation, you would see a rewrite from store frame, one constant, two constants, then an add. We prefer to just keep a separate value stack. So whenever we see consts, we just push them to a separate value stack. Keeps things simpler and a bit more optimized. So I've defined a stack. I've said that a program, in the case that we're going to load the initial program, the program is a list of instructions without any specific separator. This is a built-in feature. I'm going to say if I see an empty list, get rid of it. If I see an instruction and then a list of instructions, I'm going to do this squiggly arrow thing, which is going to let me, this is what lets me do this dot notation that I, so basically dot means here's a list of these squiggly arrows things. So I'm matching on the head, and then there's all this other stuff. So you can see the K cell as containing a list of these, a const list with this squiggly arrow thing. It's not really a const list because it's associative, but it's similar. To the stack, we're going to push stack items, which we're going to annotate with their type. Types can be i32, i64. Also want to show this. This is nice. So you can define functions. So if you want to do a sort of fairly, define your helpers in a more functional programming style, you can just say, here's a function chop. It's going to return something of type int. We're saying something of type int might be chop that takes a type and an integer. And then we write a rule that says if we see i32 and I, then we do modulus 2 to the power 32. If we see i64, we do 2 to the power modulus 2 to the power 64. And note that you don't need to give any configuration here. This is not at the top of the K cell or anything. So that means wherever, whenever, if I just want to, make sure I'm in the right bounds with my integers, I can just call chop in any cell and in any configuration.
And the type int is the mathematical integer.
Yes, exactly. So we try to just make sure like our invariants are like if you push something to the stack, it's always in the unsigned range of that data type and so on. So,
are these rules of Wasm, or are these rules that you added to make your life easier when you code the rest of Wasm?
a little bit of both. Like the specification has a lot of these things that say, well, you know, it groups like add and sub and mul as bin ops, and then it calls the corresponding bin up. So we try to stay sort of faithful to that, but we're not following it like by the letter. I'm not sure if chop it's called chop. I think that it was called that in KEVM, so we just kept, or Everett kept that name. But I'm sure there's a similar function there, because I mean the notation of the Wasm spec is actually pretty close to how you would define things in K. So that's pretty nice. Oh, and also I have defined an instruction that says if I see a const at the top of the stack, or at the top of the K cell, just push that to the stack. And then I've given the syntax of 3 instructions here. And here I have a little example program. So I'm just going to show you what happens if we run that.
Compiled to Java?
The backend is Java, which there's like 4 or 5 different backends. Okay, so what happened here is that the program got parsed. It took the first instruction, heated it with this little arrow here. That was an i64 const. It matched this rule, so it pushed that to the top of the stack. It got to this rule, and it said, well, now I have a memory instruction at the top of the stack. I have a squiggly arrow, and then the rest of the program. I don't have any rules that match that. Execution halts. There's nothing I can do from here that you have shown me how to do. So the first instruction we're going to do is just allocate memory, and I'm not going to type that up. I'm just going to copy my little cheat code here so we don't take too much time. But this actually shows a really nice feature of K, which is, you know, the configuration is sort of an XML-ish spec, right? Oh, sorry, actually, remember, I need to also extend the configuration to match. So we had so I'm going to extend it like this. I'm going to say there's a frame, my current frame. The frame contains a module. And in the module, I'm going to have a map of addresses to a memory. But for now, for version 1.0, it's always going to be a map, either an empty map or a map from 0 to something. There's no other things allowed. But you know, it's nice to use a map to make it extensible. Then we have a store. The store is going to contain a bunch of memories. And here's a nice thing. I can say that this mems cell is going to be a map. So I'm saying, well, it's going to contain memory instances. There might be 0 or more, like the multiplicity thing here. And I'm writing type map, and that just means mems is going to become a map with this as the key. So with this configuration, I'm going to be able to say, oh, I'm going to look up mem_inst with the mem address 10, and that's going to give me that element in the store. And just I have this to keep track of, you know, if we're allocating new memories, what's the next available slot. I'm going to show you how the memory allocation works and hopefully become clearer. So if we see memory, this instruction, we're going to rewrite it to dot. Dot is just, you know, remove it, basically. And we're going to look in the configuration and say, well, mem address. We can't allocate memory if we already have memory allocated. So here we are assuming that our address is just an empty map. There's nothing already there. If I try to allocate memory again, this rule wouldn't apply because there's now something in there, namely this, right? 0 points to next. Where do I get next from? Well, I look at next mem address. And in mems, I'm going to use this syntax to say, I'm going to put a new cell there. So you can actually like use this sort of XML programming style to create new parts of the configuration. This is really nice if you're doing, like in C, they use this to emulate threads, for example. If you create a new thread, we just have this pool of threads. And if you create a new thread, then you're going to add a new thread to the configuration, and then you have rules that just say, you know, they match on any thread. And that gives you a nice model of non-determinism. Like, you know, any thread can be run at any time. So also, oh, I should mention, so I don't have to write like store here. I don't have to write frame module and so on, because there's only one cell like this. This is nice. It's modular. Like if we want to change the configuration or move things around.
This is a difference to how pattern matching would work in many programming languages, right? Like Haskell, or
Yes.
where you always would need to talk also about the irrelevant parts in order to match the whole thing.
Yes, exactly. Yeah. So this only matches on the things I've specified, and everything else can be in any state. I don't really care. It's also not really pattern matching, which takes a while to get used to. It's unification. So I'm going to show you an example of that in the grow operation, where we have two rules that might apply. And that means which one applies. Well, it's basically up to the interpreter or the program. So this one we can write. So also I should just compile this to show you how that would look. So remember, we just push a const to the stack, then we allocate a piece of memory. That means the program's going to look. Oh, I didn't save. Sorry. That's one annoying thing. It's slightly slow to compile and run. Let's see. No, it's not auto-scrolling anymore either. There we go. So it consumed the memory operation now, and you see it changed mem adders, and in mems it pushed this new item. So remember, here's the map syntax. So this cell now maps to, is a key to this memory instance.
Can you forget one of the ... and see what is the error? Is that helpful?
So
I'm just curious about,
which dot?
I don't know. Remove one of the ...
Okay, so
to see what the compilers say.
So well, if I just remove it, then this wouldn't work, because what I'm saying here is that
I want to see the error.
Well, it's not an error. It's just saying, well, this doesn't apply, because you're saying if the K cell contains only memory, if it only contains the memory operation, then you can apply this rule. But actually, it contains memory and then something else, right? So the ... dots would mean, something more, right? So we're saying, rewrite whatever is at the top, and then there's more things here, and just keep that. Does that make sense? Or I can remove some other dots if.
But I mean, when you compile now, it means it run. It did something, but it's not what you wanted.
No, yeah, exactly. Because if I remove the dots here, I'm saying the K cell should contain exactly memory.
Yeah.
Whereas if I say this, well, the top is memory, and then there's.
And if you remove the other ones there.
Here.
Yeah.
This one should fail, because in the configuration I put a size.
Yeah.
So.
The size there.
So I'm not sure exactly how it would deal with that. But again, usually we would put dots in wherever we can, just because if we're adding more cells, we want them to just get the default value. Okay. So also K. One thing I should mention about K is that the error messages aren't always great. So closed parent cell missing required children mem size cell while executing concrete configuration. So that's what it says if you're. So but then again, like whenever I say, oh, this error message is bad, I just message them and they will usually fix it.
It means that when you have the dot, it could be either changing the semantics because you forgot it, or it doesn't compile because you forgot something else.
Yeah. So what you're doing is this is your definition of the semantics, and if there's a mistake in there, then that's a mistake in your semantics. Or like if you're like us, we're modeling another language, hopefully we would catch that in there.
But here the dot is like it wants to make your life easier, but it might.
Yeah, exactly. So I mean, and this is a pretty young language, so there's a lot of we prefer to code in one way in WebAssembly, but there's not. There's different ways to do things, and what's the best idiom is sort of an open question.
I mean, if we go one line up with the cursor.
Yes.
In this line, so I think the thing to get used to in K is that what this here says is that memory and something else is rewritten to dot and something else.
Yeah.
So you could kind of distribute the dot 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 over the rewriting, and that would be the classic way.
Yeah.
Right?
So.
That would be the classic way of writing it. Yeah.
Okay.
Yeah.
So you're rewriting the first thing and something else to another thing and something else.
Yeah,
Yeah.
that makes sense. That makes
Yeah.
sense.
So I think this is the. So I mean, it becomes really tedious to always write this, but I mean, yeah, definitely. I think, if I'm not mistaken, this should be the exact same thing as if we're doing it with just the dot dot dots.
Yeah, all right.
So yeah, that's what's going on. Should we do one more? Might just.
And that means you can, for instance, you have the whole configuration consisting of many things, and you can say, I rewrite this to this, and I rewrite this to this, and you don't say the rest.
Yeah, I understood that.
Okay, and I'm just going to throw in memory size. I'm going to implement it here. That's pretty simple. It goes into the store or your mem address, goes and find the corresponding memory, and guess its size. But here's an interesting one. Actually, I might actually just write that one. Yeah, memory grow. So this one is interesting because it has two rules, right? Because I'm saying, allocate more memory. Well, what's the semantics of that? Well, does that succeed? Well, it depends on your embedder. Like, where are you? Do you have any resources available? So the semantics say, grow your memory. If you call grow memory, then call this function. That can fail with, I think, a trap, like an exception, if you try to grow your memory out of like too larger than 2 to the power 16 pages or something. That's like 4 gigabytes. But if you try to grow too large, then this can fail with an exception that you can't catch in WebAssembly, but you need to catch in your embedder. Or it can just fail for whatever reason, and then you're going to put -1 there. So both these, like, again, here we come to the patch and match. Like, which one should apply? Well, actually, either might apply at any given moment, right? So if we were to implement that, it looks something like this. Also, this is an interesting example. We have this folded syntax, right? So memory grow, like here I have written it with the folded syntax, grow it by 5 pages, right? That's the same thing as that. Push something to the stack and then call the grow function, which is unary, so it's going to consume the first operand. And that's really straightforward. So you say at the top of the K-cell, you see memory.grow, some instruction. This is again typing. That would mean first do that instruction, then do regular memory grow. Yeah. I don't think that needs any parentheses. And then we're going to handle the second memory grow. So if we see memory grow at the top of the stack, then we're going to return the size, right? Like the old size. Yeah, so you see what happened when I did the unfolding, it took this, evaluated that first, put 5 on top of the stack, and now we're here. So if I want to do memory grow, that's going to be an I32 const size. What is size? Well, we're going to get to it. The stack is going to contain, well, we can only grow with, you can't push an I64 here, so we're going to grow it by some value. And then we have a stack, and we're just going to write that to the rest of the stack. So notice here we don't actually have any dot dot dots, because we're saying get the top element of the stack, rewrite it to, just whatever's left. So there's no dot 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 here. We're just actually matching on the entire list. So because we're assuming here that it's not an empty stack, because then we couldn't call this function. Our general approach is we say that we assume that we have a validated program when we're doing this, because there are Wasm validators and we're mostly interested in execution. So we want to give the correct semantics for valid programs. We would go in mem adders, and there we would need to find a specific address. There can only be one, right? Then we find the memory instance with that mem address. And that's going to have a size. And we're going to rewrite that size to size plus, we call it v. Right? So notice we're returning the old size and we're pushing the new size. Yes. Also, I want to just give one more thing here. Like, you can do this. Requires that size plus int v is less than int 2 to the power 16. So this rule only applies if the memory doesn't grow larger than this. If we do that, that should work. Famous last words. But I also want to give you this one, right? Just copy this. Yeah, so that worked correctly. Like, now we could consume the entire program. And we have grown our memory, and we pushed the old size to the stack and everything. So now we could do all these operations. But I just want to give you this one as well. You can just ignore that. Same as Haskell, right? Just use underscore. For any reason, it might fail, right? So we just put a rule for that. And that means, in our case, either this rule could apply or this rule could apply. Which means that if we would run a prover on this and would say, you know, this would always rewrite to this, it would actually try both paths if it can see that both these rules can match. Yeah, that works. So, I mean, it's non-deterministic.
Which one returns? Which path will return?
So now it returned this path where it actually grows the memory. So I tried this yesterday, and then it was the first one. Then I tried it this morning, and then it was the second one. So I'm not entirely sure. I think it might just if you compile one version, it's going to reuse whatever it had before. That's the point of, like.
But if you run it twice after compilation, you get the same.
I'm gonna run it twice. No compile.
Oh, just run it again? Oh, I think the run is actually, you know, it's pretty deterministic. I mean, it uses Java or Haskell in the backend, so it doesn't actually do any random. This is mostly for reasoning. Let's see. I'm gonna move it. One more try. Anyway, in that case, you know, the memory wouldn't grow; it would push -1 to the stack. Again, the point is that it's non-deterministic. So.
Right, but this will be the question in the simulation. If you run a simulation, then and you have a non-deterministic rule, then it will always execute the same, or it will try different. Like spin, for instance, will try different things every time. So
krun, like the interpreter, just I think it picks one. I mean, it compiles this to Java or Haskell, so it's just going to pick one of them. But if there's a command called kprove, which, I'm not sure I have this running, but if you would run kprove, it would say, and you say, here's a property I want to prove, then it would try both paths.
Okay. Yeah, so basically when you're proving, you prove for all possible steps, but when you simulate, you get only one.
Yeah.
That somehow it shows that you know.
Exactly, right.
But is that a feature? I mean, I would rather know that it is not deterministic, because I might not know that my semantics is non-deterministic.
Well, so again, what we do in Wasm is, like, for all cases, actually how we deal with this is that we just add this cell. So if we're doing verification, then we might want to say, you know, memory shouldn't just fail to grow. Or in the future, we might say, well, here's the total amount of memory we have accessible, and if that goes to 0, then we will choose one of these rules. But basically, in the configuration, we try to put things. So if you do verification, you would want to be able to toggle, right? Saying, do I allow this spurious memory fail? And so we would put configuration set like this that would default false, and then we would say this rule only applies when that value is set to true. And I mean, you can imagine a more complex case where, you know, we allocate a number of gigabytes of memory first, and then we say, well, and whenever we grow the memory or allocate memory, we shrink that, and then we say, well, this can only happen if we're out. So here I think we actually have it managed to run kprove spec. Let's see, I tried to show some property. Yeah, I didn't actually have this prepared, but here, for example, you see I try to prove a property. You give properties in this rewrite semantics. You're saying if I have something in this configuration, it should rewrite to this configuration. And then you tell kprove, please show me using C3 and SMT solvers that and symbolic execution that this will always rewrite to the right thing. And in this case, it halted and it said, well, I have 2 counterexamples for you here that I can't really prove match your property. And kprove is sort of low level. That's like what you're. That's what K actually gives you. But if you're doing smart contract verification, there's a much better tool called KLab, which uses kprove under the hood, but gives you these branches saying, well, on this execution branch, I managed to prove it, but not on this, and you can step through your entire program and your execution and so on. We're just trying to get that to work for KWasm, but it's a bit of fiddling to do. Yeah, I'm gonna stop there and just tell you where we are. Future direction. So we're still working from a bit of it's still prototypal. The memories, the things I showed you, is merged, growing and sizing of memories and so on. I have a PR that should merge pretty soon on storing and loading memory and so on. It's really quick to implement, but coming up with the right design and reading the spec closely takes a while. So. We haven't done anything with floating points because it's slightly tricky, and it's actually not necessary for Ethereum verification. They only use fixed point. There's this thing called tables, which is a way to have function pointers, which we haven't gotten to. And we actually don't have modules yet. I told you everything's a module, so we can't actually run any real Wasm program as of today because, well, we can run the empty module, I think. But the rules for grouping modules and putting them into the configuration are pretty involved. So that's maybe the next step. Yeah, and then to actually get to the Ethereum version, we would well, EWasm adds gas metering, but otherwise, the EVM is very Ethereum specific. And what we want to try to do now, and what EWasm is doing, is we have this other virtual machine. We just put a few things on top of it, and we should be able to do it without actually touching the Wasm semantics. And that's also going to be pretty cool because that means we can do. We will dynamically alter the Ethereum part of the configuration for KEVM, which can give us nice models of things like sharding, if you're familiar with that in Ethereum. So hopefully it's going to be pretty powerful. We would like to build a repository of verified Wasm contracts. Like Everett told me in the beginning, when you do this and show it to people, people are going to say, well, so you've made a Wasm interpreter. But the point is that once you've built that interpreter, you get these nice proof facilities, and we want to get to actually proving things. So, any further questions?
Good, thank you.
So I have one top level question and another more technical one. The top level one. You seem to be looking a lot into WebAssembly and Ethereum. One of the creators of WebAssembly has his own blockchain company called Definity.
What's it called?
Definity.
Definity.
Yeah, and the company is about doing blockchain on WebAssembly. So maybe that's something. Maybe it's not that way. Maybe that's something that you should look into.
Definitely, yeah.
Yeah. But the more technical one is the good thing about K, or at least when I read the paper that you showed on the slide, was alright, so you have a specification, you have executable specification, and then the proving tools all at once. And that's great. But then, and then I was thinking well, we can use the K framework to get a reference implementation, and then we test, we can do testing or whatever else to see if all the ones up there don't have bugs and so on. But then when you show this thing about being non-deterministic, usually the non-determinism in real system will get decided by the system configuration, right? So you would like a way to resolve the non-determinism in your specification with the state of the system if you want to compare, different implementations. Do you see an easy way to do that within the framework?
So I'm just trying to make sure I understand the
Let me
question
give you a
correctly.
quick example. I have a WebAssembly interpreter written in C.
Right.
And I have your thing, right? And I know that your thing is correct because you verify and so on, right? But you don't want to go formalize the one in C. Okay, let's do some testing, random testing, quick check testing, or whatever, right? Then you want to run the interpreter in C and your interpreter from K with the same system state and see if they're responding the same way.
Right.
Right.
Assuming you can get all the relevant parameters that C uses for.
The system state,
Yeah.
But the question is how you map the system state within the decisions that your execution needs to take, because if you have a non-deterministic choice, then you need to say you go left or you go right.
Well, so whenever you have that system state or whatever relevant state you want in your configuration, then you can match on it and say like I did with the spurious state thing. I'm saying, well, we often try to make sure that only one rule applies in most situations.
But can you map that to the external world?
So yeah, if you can put it into the I'm trying to think if there's some nice dynamic way to make sure that K reads the system configuration.
Yeah, that's my question.
Or otherwise, one thing. The initial hack is get the system configuration, just write that as an XML and make that the initial configuration, and now you're modeling the same thing. But I don't know of any K facilities for actually interacting with the outside and actually getting these getting the configuration. But if you can put that in your configuration XML, then you're good, and then you can match on it. Yeah. So what K does with threading, for example, it has this a thread cell that has a bunch of threads, and then it just has a rule that matches on any thread, and that's the way to match threading, right? Because the model is any thread can execute any step at any time. That's pretty much.
Yeah, and that would be another example of a system because the system could be part of the system could be a scheduler, which is kind of external to the language, right?
Right.
And then the non-determinism is just not assuming anything on the scheduler, even if the scheduler is deterministic, but we don't know it. So the language specification is not deterministic. But I think you have a very good point. The testing becomes it's a big question to the testing. How can we test in
because my question is you don't want to use maybe a priori you don't want, or at least you could use your K referencing as a reference implementation for other things that are already run into discover bugs. So
But an initial point of K, what they did early on was when they formalized C is they show that, well, if you read the specification, there are a bunch of is multiplication is that it's strict, but does it evaluate your right hand side first or left hand side first? And I think if you try to do variable modification of some relevant variables in the right hand side or left hand side, then you start it's undefined. But there's all these edge cases, and I think that's the strength of K. It's you can show your assumptions that work if they work in GCC and Clang, if they all implement things the same way, but the specification says this could go both ways, then you can implement both. And if you want a deterministic behavior there, then for that specific case, then you could, say execute the left hand side first. Or you could definitely implement a scheduler in K, but that might. But then again, you're not accessing the actual system scheduler.
Part of the language semantics.
Yeah.
Because it's
yeah. That's a good question.
What kind of property are you planning to verify for Wasm, and what kind of properties have been verified for smart contracts?
So, Wasm, I haven't actually thought that much about. I'm thinking more in terms of EWasm, get a smart contract running on EWasm and then verify that. But I mean, we will probably try to reach out and try to find is there any interesting properties to verify, or programs to verify of WebAssembly in general. This kind of contracts. Well, for example, like the DAI stablecoin, which is a pretty complex group of like interacting smart contracts, has been verified. Like it's been verified is of course like a very strong claim, but like a lot of the core functionality has been verified, and like all the functions are shown, like they can never get into a bad state and so on.
So kind of functional correctness.
Yeah. Actually, let's see here. So there's so I think it's runtime verification, verify smart. So they have this little repository if you want to check it out of like different things they have been verifying. Like ERC20 tokens. Like they did find some like inconsistencies in there, just saying what happens if you send 0 of a token to yourself. That the specification doesn't say anything about it, and a lot of contracts just implement that in different ways. And I think, when they did the KEVM, they even found like a lot of places where the actual yellow paper doesn't really say anything here. It doesn't say how to handle a specific case. This could be, so basically that would be undefined behavior.
It's already explorative in the sense that it lets you figure out inconsistency.
Yeah, exactly. I mean, if 2 rules apply, when you do krun like we did here, just to run it, then it's going to pick 1 rule. But if you're doing proving, and it says, and it can do this with symbolic execution. It doesn't have to be 2 actually overlapping rules. But if it has a variable and it can't say which rule will apply, we'll actually try both and make sure you always get to the right state. And also, I want to show you also the you don't have to write this K like this in a K. No, you need the syntax, but you don't need to write it in K file. So here's what the actual semantics looks like, what we're working on. So we're using the literate style, and we just if you look at it raw, it looks like that. So we just have these little code blocks, and those are the ones that we use pandoc to just turn that into a K file. But you can read it pretty well. So I mean, if you're interested in WebAssembly and this seems like a bit thick, then come check out. So here's our configuration. Here's exactly what I showed you. If we have instructions, then we how we sequence them. Traps are like executions. So a Wasm program can trap, which it can't catch on its own. That means it gets propagated to the embedder, and it has to be dealt with there. So. And of course, we don't implement add and sub and mul as separate ones. We can do a bit of nice abstractions, with making them unop and binop, and then we do the stack manipulation stuff. And you see, we have all the floating point is just commented out for now.
So, how certain is it that if you will go to WebAssembly?
Oh.
What do you think? They may or may not.
Well,
thinking about it.
I'm on record here.
Okay.
I don't know, but I mean, what I can tell you is the EWasm team people from the EWasm team join our weekly meetings and everything. So I think, especially the gas metering is something people are really excited about. So you would be able to, know beforehand the amount of gas that a function call would require, which is really hard with, or maybe even next to impossible with the EVM, where Wasm allows some more metering and some better static analysis. So I think, well, if you can show that very clear value, then I think this is going to happen. There's already a test net. There is EWasm running, but it's just a test net for now. So I'd say 90% sure, unless there's some weird snags or the Wasm team does something very strange, or they run out of money. That might be the that might be the most
gas,
likely.
Yeah.
We-
Only the gas, the meta gas.
Mhm.
Yeah.
Yeah. I mean, it's not a huge amount of people working on it, so it's the truck factors aren't really that big for these projects. But
Hmm? Yeah, thank you.
yeah. Right. Thanks for coming.